So welcome back. In this video, we'll start with performance calibration, focusing on OCV calibration, and it would be split into multiple subparts. In this video, we'll talk about one of the interesting databases which can be useful for deriving parameters called Liiondb. In the previous videos, we've covered battery database and parameter update options within PyBAM, and the type of models it supports, including DFN, SPM, SPME, and ACM, and the differences between them. In this video, let's begin with the Liiondb, what Liiondb is, how it is useful, and how we can integrate with Python code and PyBAM. So let's begin. And now, before we jump into Liiondb, let's understand the complexity and the motivation, right? So now this image is taken from Chen 2020, which is one of the uh, breakthrough literature which came up recently. And it goes into the detail of parameter estimations, and they did a thorough study with experiments and literature review and found out that P2D models is very complex, and it it requires 35 plus or around 35 parameters to be estimated to build a confident model. And definitely that's not easy. It's not possible to do all those experiments and for commercial reasons, right? Now this image shows what some of those parameters were. So it includes thicknesses, porosities, radius, Brugman, exponent, uh, concentrations of lithium in different sections of the cell, OCVs, OCPs, activation energy, reaction rates, diffusion, conductivity, and so on. So the list goes on. I won't go into the details of each of these, but just imagine if you were given, or if you were given this task to determine all these parameters through experiments or through literature on our own. It would be very confusing. Now, traditionally, this is how we would do it. That is through literature review, right? So let's understand the challenges there. Now, this is me trying to open a paper to find out one of the parameters that I was looking for. That paper, in turn, had 10 different references. So then I go into some of those references, and then after a bunch of different confusions, I end up spending a lot of time. It's already 2 a.m. and I am still not able to find out confidently the value of that parameter. Hope this is relatable, right? This is research. Now, I feel this is equivalent to our very own favorite Tom and Jerry, which is where there was an endless chase by Tom trying to catch up Jerry, equivalent to doing research with uh, looking at one of the research paper which has a supplementary data, then the citations links to some other paper which indeed links to some other papers. It's an infinite rabbit hole, right? And it sometimes feels like Interstellar is something we are living in reality. So time dilation is real, right? We think we will spend 10 minutes finding the OCP value of certain chemistry, but we end up spending 3 days to find the same, and still we don't have confidence in the value, because we don't know what whether the paper that we have found out is a reliable source or not, and if it's trustable for our use case or not. And that's completely uh, understandable. Now it's not always our fault uh, or unawareness of the right literatures, but sometimes the literature itself would be faulty, right? You can't blindly trust a literature because sometimes the actual paper could be completely off from the reality, which is the literature review itself. It completely depends on the researcher, like who is doing the research, how it was being conducted, whether it's reliable or not, and trustable in the community or not. Now, having said that, this was the traditional way. Now, with the rise of Gen AI, we usually don't do these research manually, right? Google search is being transformed to Gen AI prompts and deep research. So let's see the other face of it. Gen AI relies on data available on internet. Internet is filled with bad data along with good data. And it's hard to identify which is a good data and which one is not. So if you end up asking a question with web search on a deep research, then it's a possibility that you might end up getting the output from one of the bad data available. Now, battery is an emerging field and there's not a lot of good data available online. And the ones which is available might be hard to find out if you're not deep into research and aware of what's going on. So it's a vicious cycle. The bad data from internet can end up being your output when you write a prompt to Gen AI. So we need to be careful about that. Now, Gen AI, although might give bad data, but it's always confident, right? It's confident even when it's wrong, and that's what hallucination is. So it might end up giving a value, but the citations might be wrong, right? We might end up getting the right answer, but from a wrong source. And we won't be able to justify that because we have cited a source which is not reliable and trustable among the community. Now, this is just an example, and don't worry about these numbers, but that's also a possibility to be considered about. And we might say, okay, like VAVTK, that's all right. I mean, it's giving us an answer and it looks real, it looks trustable. Why not? Let's use it. And that's the mistake we might end up making. So what if I tell you there is a database already available called Liiondb, which is a remarkable work by a bunch of researchers who have done thorough research, found out the best papers, combined the data, created a database, and made it handy to be used with the ease of a website which has all these data in a very interactive UI. So won't that be wonderful and very useful for us so that we don't have to worry about data collection, extraction, reliability of the source, and so on. So that's what this paper brings about. So this is an open access paper. You can download and read through it. I would like to take a moment to appreciate the efforts of the authors and would like to cite this before we move ahead. And there's also a small nice video which you can refer to get used to the interface. There's a link which is broken, but if you search for, I'll drop these links in the comments so you can in the description so you can go through it. But it's just https://liiondb.com. Even if you type on Google, you'll be able to redirect yourself to this link. So this is where we are. It's a very nice, easy to use Streamlit app. Within parameter dashboard, you can find out. So on the left, you can see parameter dashboard, which we'll go through. Then advanced queries, as example advanced queries. So it also has some examples to get started with and understand how to give a query for extracting some of the outputs that it contains. Then you can access the Liiondb from here with some examples, and then you can also contribute if you get familiar. And then the links to other relevant pages are mentioned here, along with the architecture that they have in the background for their database. Now let's come back to parameter dashboard. This is where all the magic lies. So for instance, we want to look at negative electrode output. So the list of parameter consists of half cell OCV, diffusion coefficient, particle radius, conductivity, uh, and thicknesses, etc. So the list is long. I won't go into the details of each, but let's start with half cell OCV. And then in material, they have graphite plus silicon blended electrode, or a silicon pure electrode. So let's select graphite, and then once you do that, it will populate or filter out all the outputs which has this combination. So we get a bunch of these uh, half cell OCPs from different papers along with their URLs if you want to cross check and verify, or even understand better how the test was performed. It also has a list of notes where it gives a brief idea about how this test was done. So you can refer this if you want to know, let's say, what was the operating conditions to derive this data. Now, once you have the list, you can then go to the select parameter to display section, select the parameter you want to display, and finally visualize it below in the form of a plot. You can also get the values from the array section, copy it over to Excel, download as CSV, or even add it as array in your Python code. Similarly, we can alternatively look at positive electrode half cell OCVs. An LFP is a good example because it is prone to hysteresis, which needs to be captured accurately. And by default, PyBAM has a single OCP definition, so it doesn't distinguish between charge and discharge, which works well for most chemistries, but in LFP it's not a good way to proceed. So we'll see how we will use it later on in one of the codes, but for now let's see how to extract this function. So if you see here, there is a paper column which points to the paper name from which the data was extracted, and you can see the second and third entry corresponds to the same paper. Now, why does a half cell OCV has two entries from the same paper? That's because it's not just an identical data set, but one is for charge, the other one is for discharge. So, and the test was performed at C by 50 versus a lithium reference electrode to be able to derive this. So it's a half cell OCV at C by 50 separated for charge and discharge. So that's how we can identify what our data is. Now let's plot it and see. So we can just select these two and then look at the plot and clearly see the difference between the two. And this is a significant difference, as it can even elevate when it comes to voltages with the internal resistance effect. So now if you were to extract this data, we can just go to one of them, see the function, and then copy over this function. So it has an equation with all the coefficients mentioned, and this is a function which can be easily pasted in Python to be used as is. Just a quick note, PyBAM accepts function. So this is exactly what you need. You just need to set the according charge and discharge OCPs, which we'll look at in the next video by just assigning it this function. So this is ready to be used in PyBAM and Python. Now this is the interface. Now let's quickly take a look at how we can actually integrate it within our local Python. So to be able to set it up locally, you can either manually download this GitHub repository as zip and extract it in your local folder, or you can alternatively install or create a clone using the following line of codes. So to begin with, you can just install all the libraries present in the requirement sheet. So if we go back to this section, there's a requirement.txt which has a list of all the libraries required. You can either manually install them. Alternatively, you can have this line of code which imports system and then uh, installs particular version of SQL Alchemy and scicopg2, which would be used in this exercise. And we just need to make sure that pandas and SQL are 2 point something to avoid any error due to library mismatch. So once that is done, we can use this option. I already have this folder created, so I will comment it out, but when you run this line of code, it will basically copy over the latest zip file from GitHub library, which is this link, into the folder which contains this Python notebook. So for the interest of this exercise, I'll comment it out, and then it will basically link these libraries. So this is just a syntax we need to copy over, nothing much to worry about, but it's just the architecture. The Liiondb folder consists of a functions folder. So if we go inside, we have a functions folder with fndb, which we are calling out here and storing it as fndb. And then within that fndb Python file, there is a method which is liondb, which we are calling out to assign two variables. So it returns a database which is stored in this data frame DFNDB, and then a connection link stored in DB connection. So with this, we are all set to get started with the queries. Now, before understanding the query, let's see some examples, what you can extract from this. So the first example is to get this is the first one, which basically extracts all the So it basically extracts the OCV curves for cathodes with higher nickel content more than 50%. And the filtering option are basically shown in the last two lines. The remaining lines will come back to shortly, what it means, how it's set up, etc. But for the time being, let's just focus on the output. So once you run this code, it takes two inputs. So the structure is pd.readsql and send the query and the database which we created, and then it creates this database based on this filtering and stores this in the data frame, and then we can look at the first few lines using .head option to print it. So here we can clearly see we only see high nickel content materials and their corresponding OCPs or half cell OCVs. Then similarly, you can do lithium diffusivity in graphite that are valid at 10 degrees Celsius with the help of these filters. See all the separator porosities across different literatures, and then find out what's the median or mean porosity that you would like to go ahead with, and so on. So similar examples you can find in their website. So in the example advanced query section, you can find all these queries, so feel free to check that out. Now coming back to our use case, which was how to define the query, and then eventually extract OCPs of LFP for charge and discharge. So before we go into uh, the OCP section, let's understand how the query is laid out. So we'll come back to this image which we saw earlier, which is the architecture of Liiondb. So Liiondb in the background has the following architecture. It consists of a main data section, which has some subsections for parameter, paper, method, material, and so on. Now imagine you have two sheets. Sheet 1 has data, sheet 2 has paper. Now sheet 1 consists of data which has data ID, paper ID, and material ID. And you are given a task to find out what's the paper tag of data ID 1. So if you see here, data ID 1 corresponds to paper ID 101 and material ID 5, but there is no paper tag here. So the way we will find it out is find the common link, which is paper ID, find the value of paper ID, and then map out what corresponds to data ID 1. So that in this case, it corresponds to Smith 2020. So this is how you link a certain input when it's not there in the given sheet. This is exactly what Liiondb does and expects in the query. So if you see here in data section, there is data ID, paper ID, parameter ID. And if we were to find out what's the DOI of a paper of all the papers which has material ID set as LFP. Now material doesn't have a paper tag or DOI, and paper doesn't have a material ID. So the way we will link it is through this data section, which is the central power of this structure. So this is what we do. We ask for all that we want as select distinct, which means avoid any duplicate values. Then we ask for parameter.name. So parameter is the header and the sub variable is name. So we say parameter.name, and we can assign any string to it. So we can call it as parameter, and the same would appear as a header in the final table. So we assign it as parameter, paper.paper tag as paper. Then we want the DOIs or URLs of the papers. We want notes whether how that OCP data was extracted, and then we want the OCP functions. So this is how it's laid out. And then to link these up, we need to define this line of code. So it says from data, join paper on paper.paper ID equals to data.paper ID. So the common link between paper and data is paper ID. So if you see here from paper and data, paper ID is the common link, and that's how we link it. Similarly, for material, the common link is material ID. So that's how this line is laid out. And similarly, this line signifies the linking of parameter and data section with the help of parameter ID. So once we have linked up all these, we are ready to go, and this we just need to apply certain filters. So we only want the outputs where parameter name is half cell OCVs and material.lfp is set to 1. So that will give us only the LFP half cell OCVs. So with that, we end up getting this table, and this table has the same structure that we saw in the website, and it has half cell OCVs of taken from all these papers. Let's say we are interested in the first one. So it's now stored in this data frame with the same command as we saw earlier. So all we need to do is take the first index and the function from this df. So this simple line of code will help us do that. So print df.location 1 is the index, column is function dot decode, and there you go. You end up getting the function that we intended to use, and now this can also be assigned directly to a pybem variable which stores the OCP for charge or discharge separately. So hope this was useful, and in the next one we'll cover the integration of this function with a pybem model and then see how the results look like. So thanks for watching. See you in the next one.